Here we have notes for chapter 3.3, the first derivative test. So let's just go through some of things that we already know, just for review. Now, what does derivative represent? Derivative simply represents the slope of the tangent line to our curve or to our function, the slope or the steepness of the point on the curve. When the function is increasing, then what is common about the derivatives at those points? Well, if a function is increasing, then our slope is always positive, and we can say our derivative is always greater than 0. When the function is decreasing, what is common about the derivatives at those points? We know our derivative or our slope or steepness will be falling, so f prime will be less than 0. Our derivative function will have values in the negative, smaller than 0. Right. And when f prime is greater than 0, our function is increasing. If f prime is negative, we know our function is decreasing or falling. When f prime is equal to 0, then our function is constant. There's a horizontal or the graph is changing direction, either from down going to up or from up going to down. But we have a point there where the slope is 0, where the graph levels off. Okay, so the first derivative test is to determine using f prime, using the first derivative function, to determine where the graph is increasing, where it's decreasing, and also so that we can determine whether the graph has a relative maximum or a relative minimum. And the way we do that is we look at whether there's any change in slopes between at those critical points. So first thing we do is we find the derivative, we set it equal to 0, find the critical points. Now, critical points can come from, again, both denominator and from numerator and denominator, so we need to take both into consideration. Critical points also exist where the function is not differentiable, so sharp point, that's where the denominator of f prime can come into play. Next thing we do is we put all the critical points on the sign line, because those are all candidates that we need to test. We test the interval after we create a sign line. With critical points, we plug values into f prime to determine the slope. So we choose a value in each of these intervals, plug them into the derivative function, and if we get a positive value in the derivative, then we know this region will be positive. We know that this region, the graph will be rising. If we get a negative, then we know that our graph during this interval between these two x intervals, the graph will be falling. And if we get a positive in this region, if we plug a value in this region into the derivative and we get a positive, then we know the graph will be rising again. Okay. Now, if a graph is rising and falling, and let me have another instance. Then we can say we can determine relative max and relative min by looking to see if there's any change in signs. But first, we can say that our function is increasing in the interval, from negative infinity to a, and then from b to c, because f prime is greater than 0. Okay, so many times, especially free response questions there's some free response questions of your AP exam where they will ask you to determine or to show in words why a function is increasing. So these are the words and the notation you have to use. We can say our function is decreasing in the interval from a to b and then also from c to infinity because f prime is less than 0. We have a negative slope. Relative maximum is going to occur in this case at a because our f prime changes from a positive to negative. And also at point C, because there's another change in signs from positive to negative. Relative minimum is going to occur, in this case at B, because the slope changes from negative to a positive. So any valleys in the graph, we can visually see that will be a relative minimum. Any hills of the graph, we can see those will indicate relative max. Let's look at example 1. Determine the interval at which the function is increasing and decreasing. Locate the relative extrema. So we go through our steps. First thing we do is we find a critical point. To do that, we find the derivative. So the derivative of 1/3 x cubed becomes x squared because we bring down the 3, and the 3 and 1/3 will cancel out. 5/2 x squared becomes 5x. Negative 6x becomes negative 6. Negative 3 goes to 0. We set our derivative now equal to 0 to find our critical points. We factor, we get x plus 6, x minus 1. So we get x equals 1 and x equals negative 6. We put those on a sign line, and then we test each interval because we want to know where the graph is increasing and where it's decreasing. So in this interval, I can choose any value that is to the left of negative 6. I'm going to choose negative 7. So plug negative 7 into the derivative function. I'll get negative 7 plus 6, which is negative. Negative 7 minus 1, which is positive, negative. So two negatives multiplies gives me a positive. So I know that in this region, my graph will be rising. My graph will be increasing. In this region, I can choose 0. It's an easy number to choose. Plug 0 into the derivative again. I get 0 plus 6, which is positive. 0 minus 1, which is negative. Positive times negative is negative. So I know that my graph will be falling. Here I can choose 2. That's a value that is to the right of 1. I plug 2 into the derivative. I'll get a positive. 2 into the derivative, I'll get a positive. Positive times positive, I get a positive here. So I know my graph will be rising, falling, and rising again. So we can make a complete statement about increasing function. Our function is increasing on the interval from negative infinity to negative 6, and also from 1 to infinity, because simply f prime is positive, greater than 0. Our function is decreasing on this interval from negative 6 to 1 because our f prime is negative. So negative derivative indicates that the graph is falling. Relative maximum occurs at x equals negative 6. Negative 6, because f prime changes from a positive to negative, the graph is rising, and then it falls again, so we know there's a relative max there. Relative minimum is going to occur at x equals 1, because at x equals 1, we see the graph changes from a negative slope to a positive slope. So with these arrows, you can visually see that how the pattern of the graph will go. Okay. One more thing is that these ordered pairs are coming from the original function. So once we determine that there's a relative max at negative 6, we plug negative 6 back into the original function, and then that will give us the physical location of that point, which is at 51. If I plug 1 into the original function, it'll give me a decimal value of negative 6.167.